Okay, so we are to lesson 4, and this is an extension of lesson 3. This is going to have us solve more complex equations, quadratic equations using factoring. The more complex part, if you look at example 1, is that the leading coefficient, our a value in this quadratic, is not 1. So this kind of throws a wrench into our factoring a little bit. So I'm going to give you steps. This one has a little more guided practice because I feel this is tougher to pick up on. So it's important that you pay attention to this. So to do this, I'm going to keep it similar to how I showed you to factor before. The first step, though, is a little different. The first step is I'm going to multiply my a value by my c value, meaning 2 times 7, which is 14. And then I still have 9 on the bottom. So my factoring, in my brain thinking here, numbers that add to be 9 multiply to be 14. Numbers that add to be 9 and multiply to be 14, 7 and 2, or 2 and 7. It does not matter. So when I write this out, I'm going to write out x plus 7, x plus 2. Okay? Looks simple enough right now. This is the part that I think is kind of complex. What you do in this next step is you divide these constants both by that a value, okay? So I'm dividing them both by 2 because 2 is the a value. So we see how we have 7 halves and we have 2 over 2. I can simplify 2 over 2. I can't simplify 7 halves. So I'm going to multiply 2 on the front of this expression. So I have 2x plus 7. And then I can simplify 2 over 2. So 2 over 2 is 1. So it's 2x plus 7 times x plus 1. And if you use that double distribution, you can double check to see that you factored it correctly. Now that's a little tough. But the main thing is that you factor it like you normally would, but you start off with a times c, and then you divide by a. If you can simplify the fraction created by dividing by a, simplify the fraction. If you can't, then you multiply that a value by the x value in that binomial. Now I know that's a lot. It seems complicated at first, but I think once we do a few more, the pattern starts to form a little bit better, okay? So in this next example, to start my factoring, I'm going to multiply a by c. That becomes negative 6. And then in this one, b is negative 1. So numbers that multiply to be negative 6 and add to be negative 1, that's going to be negative 3 and positive 2. Okay? Negative 3 and positive 2. So I'm going to write out my factors as x minus 3 and x plus 2. And like I said before, you divide by that a value. So I'm dividing each of these constants by 3. So what this becomes is x minus 3 over 3 is just 1. And I can't simplify 2/3. So I just get 3x plus 2. And that is my factored expression. Okay, that's my factored expression. So I know 2 problems is maybe not enough to see a pattern, but I want you to try this guided practice. If anything else, maybe just wait for me to show these again, but try them as much as you can. Try to get through as many steps as you can and then pick up kind of where I leave off when I show you the solutions. Okay, so I'm going to give you a few seconds to pause, try them, and then once you're ready, resume the video and I'll show you the solutions. Okay, so for this factoring, I know I gave you kind of a doozy right away, but multiply a by c, I get negative 60 on the top, 7 on the bottom. So my factors are x plus 12, x minus 5. I divide them by a, which is 3. I can simplify 12 divided by 3. I cannot simplify 5 divided by 3. So that is why I multiply 3 on the front. So that's the pattern. In number 2, 5 times 6 is 30. My factors are x minus 3, x minus 10. I can simplify 10 over 5. I can't simplify 3 over 5. That's why I multiply 5 on the front. So now that we got that pattern sort of down, I'm going to move on to some special cases or special patterns. So special patterns with these types of expressions, you're looking for the first and last term to both be perfect squares. So in part A, first term, last term are both perfect squares. There is no middle term. So what this will look like, 4x plus 6 and 4x minus 6. And the reason I can say that, 4x times 4x is 16x squared. 6 times negative 6 is negative 36. And if I do the plus and the minus here, that means the middle terms would cancel out if I distribute this back out. So that's why I have plus 6 minus 6. For part B, first term is a perfect square, last term is a perfect square. 3y plus 7, 3y plus 7. And if you think about it, 3y times 3y is 9y squared. 7 times 7 is 49. That's how I get the first and last terms. And if I think about it, 3y times 7 is 21y. 21y plus 21y is 42y. Okay, so first and last terms have to be both perfect squares. In C, part C, 25 and 121, both perfect squares. First term would be 5t minus 11, and then 5t also minus 11. And the reasoning behind that, 5t times 5t is 25t squared. Negative 11 times negative 11 is 121. The reason I use negative 11 is because this middle term was negative. So that would be negative 55 plus negative 55. That would result in the negative 110. So negative 55t plus negative 55t. So we're kind of reversing that distribution we talked about in lesson 2. Got to think back. But that's the idea, is that these patterns are not very common, but the main thing you're looking for is the first and last term to be perfect squares. And then you think about the patterns that we've picked up from factoring before, and you apply them when you have perfect squares as the first term and the last term. So, in example 4, I'm going to show you some examples where you can factor a monomial out of your expression before you do the factoring. So if we look at part A, in this expression, each term has something I can factor out. In part A, I can factor out 4 from each term. So to show that, call this a GCF, greatest common factor. I can factor out 4 from each term. If I factor out 4 from each term, I have 1x squared, or just x squared, minus 1. Factoring something out, you're pulling out that number and you're dividing each term by that number to factor it out. Because if I distribute 4 back through, it would be 4x squared minus 4. My factoring is not done yet. I still have to factor x squared minus 1. If we think about our patterns, first and last term are perfect squares. I'd have x plus 1 and x minus 1, because x squared is a perfect square, 1 is a perfect square. For part B, if you look closely, you'll see you can factor out a 3 and a y. I'm going to go a step further, and I'm going to factor out negative 3, y, because negative 3 fits into negative 3, negative 3 fits into negative 18, and I can factor out y from each term. So what is really left, if I factor out negative 3y from 3y squared, all that's left is y. If I factor out negative 3y from negative 18y, I'm left with positive 6. So factoring something out, you're kind of undoing distribution. That's what you're thinking of here. So if I distribute, I should get my exact same expression back again. Part C, if I look closely, I can factor out a negative 4, or sorry, not negative 4, negative 2 from each term. Sorry, 4 doesn't fit into 10. So if I factor out a negative 2 from each term, what's left is 2m squared plus 5m minus 12. The reason I factored out negative 2 is I don't like that leading term to be negative. So this is the factoring we talked about before. I factored out a common factor, but I still need to factor 2m squared plus 5m minus 12. So what happens here, just like we talked about previously in the video, multiply the first term by last term. 2 times negative 12 is negative 24. This is positive 5. So my two numbers are going to be 8 and negative 3. So I'm going to keep that negative 2 on the outside, and this becomes m plus 8 and m minus 3. So to finish that factoring, remember we divided by that a value, so we're dividing each of these by 2. So my final factored form is negative 2 times m plus 4 times 2m minus 3. And the reason I couldn't simplify 3 halves, so that's why I multiplied that 2 on the front, following that pattern. Okay? Lastly, factoring out the greatest common factor from this expression. I can factor out a 5. So if I factor out 5, I'm left with z squared minus 5z plus 8. If I factor out 5 from each term. So now this one's a little bit easier to factor. I just have to do 8 and negative 5. Now if we think about it, numbers that multiply to be 8 and add to be negative 5. Let's think. 1 and 8, not going to work. 2 and 4, not going to work. So I can't factor this any further. So really, this is completely factored. I know that looks weird because we had been factoring these like crazy before, but not every quadratic is factorable. So this is as far as we can go factoring-wise. So you're going to notice that what's going to happen when we can't factor it. I'm going to give you other methods to solve when we can't factor. So I am actually going to just have you do this guided practice right now, have you do a mini practice, and then have you come back for example 5, because example 5 is the solving, and I feel like we're getting to the kind of the upper limit of how I want these videos to go, but these are dense topics. They have a lot of information. So that's why these videos are getting a little bit longer. I'm sorry about that. I'll try and make them more concise, but guided practice, try these, try to factor out a common factor first, and then factor them like I kind of showed you before to see if you can pick up on some of those patterns. Okay, so to round out this part of the lesson, 5 and 6 were doozies. They were tough, okay? So in 5, what I would have liked you to have seen is one of two things. Either these are both perfect squares, meaning you can use that pattern we looked at before, or you can factor out a 4 from each of these, and these are still perfect squares, 9 and 4. So if I factored out 4 first, I'd have 3x plus 2, 3x minus 2, using that pattern of perfect squares. Now, relying on a pattern isn't always the best way, but it does really simplify things if you can factor. Okay, that's why I show you some of these patterns. In number 6, got a big number there. You factor out factor out a 3. I've got 5p squared, 8p, and negative 21. So I had to find numbers that add to be 8 and multiply to be negative 105. So what I essentially do to find factors of 105, I take 105 divided by 2. Didn't work. It's not an even number, not a whole number. 105 divided by 3, 105 divided by 4, divided by 6. So you keep testing numbers to see factors of 105. I got 7 and 15. Well, they're 8 apart, so they worked. And then I used that pattern we had before. So right now, I just want you to get practice with factoring. Just straight up factoring, seeing the patterns, asking questions, getting help so that you can solve later on in the lesson. This is a big lesson. It is dense. Get used to it. Algebra 2 is dense. It has a lot of information. I'm going to do my best to give it to you in a way that makes sense, but some of these videos just get long, and I'm sorry for that. So pause them, take your time, do not rush through them, okay? So you can move on to the mini practice I have for you, and then eventually you'll get to this example 5 later on in the lesson.